Today we prove the Minkowski's inequality for finite sum for real numbers x1, x2, xn, y1, y2 up to yn. We have summation I from 1 to n mod of xi plus yi power p whole power 1 by p, which is less than or equal to summation I from 1 to n mod of xi power p whole power 1 by p plus summation I from 1 to n mod of yi power p whole power 1 by p. This is the Minkowski's inequality for finite sum. Finite sum means the summation is from I from 1 to n instead of I from 1 to infinity. So let's prove the Minkowski's inequality for finite sum here. First of all, note that p is greater than 1 and 1 by p plus 1 by q is equal to 1. So as p is greater than 1 implies that 1 by p is less than 1, and this implies that what does it mean? It means that 1 by p is greater than 0 but less than 1, so 1 by p belongs to the open interval 0 1. This implies that 1 by q, which is equal to 1 minus 1 by p, this quantity is of course less than 1. So as 1 by q is less than 1, so q is greater than 1. Therefore we have q is greater than 1. But in this inequality there is no any q, but we shall apply when we apply the Holder's inequality. So in the Holder's inequality we deal with two exponents in terms of p and q. So that's why in the beginning I conclude that q is greater than 0, and this condition, this one and this one, all these three conditions which will be used in the Holder's inequality, and also these two conditions are used in the Minkowski's inequality. So I mean that the conclusion that q is greater than 1 is not superfluous, means it is not redundant, it is used in the Holder's inequality. So in the beginning we have concluded that q is greater than 1, so no need to worry about that, why we have concluded q is greater than 1. Here we deal first of all with the case 1. The case 1 is that you write here either this quantity summation I from 1 to n mod of xi power p equals 0, or summation I from 1 to n mod of yi par p equals 0. When this one equals 0, then it is only possible when each mod of xi par p equals 0. Each I, and this is possible when each mod xi equals 0, and this is possible when each xi equals 0. So when this one equals 0, each xi equals 0. So what does it mean? It means that in inequality 1, when each xi equals 0, on the left hand side we have summation I from 1 to n mod of yi par p whole power 1 by p, and on the right hand side, since each xi equals 0, so this term goes to 0. So we have this one, summation I from 1 to n mod of yi power p whole power 1 by p. So in this case, on both the sides we have summation I from 1 to n mod of yi power p whole power 1 by p. So the inequality satisfies when we have this condition. Similarly, when we have this condition, the inequality satisfies by the alternate arguments. So you can do it. I just write here alternatively. If summation I from 1 to n mod of yi power p equals 0, then for each I, or for all I, yi equals 0. So in both the cases, this one or this one satisfies, so one holds. Case number 2. Case number 2 is when both summations are non-zero, that is summation I from 1 to n mod of xi power p is non-zero, and summation I from 1 to n mod of yi power p is non-zero, sorry, not equal to 0. Yes. Now we consider the summation I from 1 to n mod of xi plus yi power p. It can be written as summation I from 1 to n mod of xi plus yi into mod of xi plus yi whole power p minus 1. Since for x1 y1 mod of x1 plus y1 is less than or equal to mod of x1 plus mod of y1, and so on for x and yn. Mod of xn plus yn is less than or equal to mod of xn plus mod of yn. When we sum all these inequalities, means by adding the left hand sides and right hand sides, so what we get in this way: summation I from 1 to n mod of xi plus uh, but it is better that if you write in the other way. Actually, we had these inequalities in this way before. Okay, now what we do, we multiply each inequality by involving their respective variables in this way. Mod of x1 plus y1 into mod of x1 plus y1 whole power p minus 1 less than or equal to the product of mod of x1 plus mod of y1 into mod of x1 plus y1 whole power p minus 1. Actually, I multiplied this number on both sides of this inequality. Similarly, when we multiply the same modulus with power p minus 1 by involving x and yn uh, on in this inequality, so we get the inequality in the same way, but for xn and yn. Xn plus yn whole power p minus 1 less than or equal to xn mod of xn plus yn into mod of xn plus yn whole power p minus 1. So when we add all these inequalities, what we get? We get I from 1 to n mod of xi plus yi into xi plus yi power p minus 1 less than or equal to summation I from 1 to n into mod of xi plus mod of yi into mod of x I plus yi whole power p minus 1. So we shall rub it. So we have this quantity which is same like that, this one. So this is less than this number. It means that by following this inequality, we have less than or equal to I from 1 to n mod of xi plus mod of yi into mod of xi plus yi power p minus 1. Yes, this implies that summation I from 1 to n mod of xi plus yi whole power p less than or equal to summation I from 1 to n. The summation gets separated over these two terms, this one and this one, so we can do here mod of xi into xi plus yi power p minus 1 plus summation I from 1 to n mod of yi into xi plus yi whole power p minus 1. So this is our equation number 2, and now we apply the Holder's inequality. So by Holder's inequality, what is the Holder's inequality? Holder's inequality is summation I from 1 to n mod of ai bi summation I from 1 to n mod of ai into mod of bi, which is less than or equal to summation I from 1 to n mod of ai or p whole power 1 by p into summation I from 1 to n mod of bi for q whole power 1 by q. So we apply the Holder's inequality on first of all this sum and then this sum. This is equal to, actually here when we talk about this sum, this is our mod of ai, and this term, this complete term is mod of bi, remember, because I'm telling you that mod of xi is mod of ai, and mod of xi plus yi whole power p minus 1 is our mod of bi, because this is equal to because this is a non-negative term, this one is a non-negative term mod of xi plus yi whole power p minus 1, so its modulus is same like that, modulus of mod of xi plus yi whole power p minus 1. So this is our bi, it means that mod of bi is equal to, if this is our bi, this one, then mod of bi is same like that bi. Okay, so here you must know that If this is bi, then mod of bi is bi. So here this one is our mod of bi. So we shall apply the we shall apply the Holder's inequality on this summation, the first summation I told you before. We have I from 1 to n, I from 1 to n, summation xi yi whole power p, which is less than or equal to, by the Holder's inequality I told that that's our mod of ai, and this quantity, the whole quantity mod of x1 m mod of xi plus yi whole power p minus 1 is our mod of bi, because its modulus is same like that. So following this inequality, we have the first summation in this way: summation I from 1 to n mod of xi whole power p, and the power of summation is 1 by p into summation I from 1 to n mod of xi plus yi whole power p minus 1 into q whole power 1 by q plus, by the Holder's inequality on this sum, we have summation I from 1 to n mod of yi power p whole power 1 by p into summation I from 1 to n mod of xi plus yi into p whole power p minus 1 into q, and the power of summation is 1 by q. So this quantity and this one are same. We can take out, when we take out, what we get summation I from 1 to n mod of xi plus yi whole power p less than or equal to summation I from 1 to n mod of xi power p whole power 1 by p plus summation I from 1 to n mod of yi power p whole power 1 by p multiply by the quantity which would be taken out, I mean this one. What is this p minus 1 into q? Actually, since we know that 1 by p plus 1 by q equals 1, this implies that p plus q equals pq. But take the LCM, then shift pq on the right hand side, then we get q equals p q minus p. is sorry, uh, you shift q on the right hand side, pq minus q. P is equal to, q is taken out, p minus 1 into q. So this quantity equals to p. You can see here, this is equal to p. So I would write here p, and this term and this term, they are same. So we divide by this number on both sides. Summation I from 1 to n mod of x I plus yi power p divided by summation I from 1 to n mod of xi plus yi power p whole power 1 by q. This is less than or equal to summation I from 1 to n mod of xi power p whole power 1 by p plus summation I from 1 to n yi power p whole power 1 by p. So this quantity goes up. When it goes up, the exponent 1 by q turns into negative, means it will be minus 1 by q when it goes up. When this quantity from the denominator goes upwards, the exponent turns into minus 1 by q, and this is equal to summation I from 1 to n mod of xi plus yi power p whole power 1 minus 1 by q. Okay, we shift this term from the denominator to numerator, and then the power 1 by q will be minus 1 by q. And less than or equal to summation I from 1 to n mod of xi power p whole power 1 by p plus summation I from 1 to n mod of yi power p whole power 1 by p. And what is 1 minus 1 by q? This is equal to 1 by p. Therefore 1 summation I from 1 to n mod of xi plus yi power p whole power 1 by p less than or equal to summation I from 1 to n mod of xi power p whole power 1 by p plus summation I from 1 to n mod of yi power p whole power 1 by p, which is our Minkowski's inequality for finite sum.